Hi, so we are Danica and Carly, and we decided to do our project on the Pythagorean theorem. And so, for me, in hopes of teaching middle school, I realized that the Pythagorean theorem is such a fundamental concept, and it really needs to be understood in order to be able to explain it not only algebraically, but also visually. And so, this is why I think GeoGebra is a great thing to kind of use this to demonstrate the concept of this theorem.
I've always seen the Pythagorean theorem in math classes, but I never questioned how it works or what it actually looks like. So I wanted to visually look at how the theorem works with different sized triangles.
So, this theorem states that the square on the hypotenuse of a right triangle is equal to the sum of squares on the two legs.
So our question is, how can squaring two sides of a right triangle equal the square of the hypotenuse no matter what the length is?
And so here's what we're going to be observing at first. And so we can see that we created a right triangle, and that is this in white. And so it's a 90-degree right triangle. And what we did was we created, so this right here is A, so we have A squared, and then this is B, so then B squared. And basically these two sums, the sum of these two areas added together is going to equal this area of green. So green represents a hypotenuse squared, it represents C squared. And so up here we can see that the area of blue, of blue plus red is going to equal green. And then due to these sliders, it's not just this triangle. Since it's a 90-degree triangle, no matter what length any three of these sides are, the area of blue plus red and the area of green are always going to be equal. And so for here, let's see. So we can make this shorter, and let's make this a lot longer. We can see that the area of blue plus red, which is a squared plus b squared, is always going to equal c squared, which is represented by green. So now that we have this proof that the area squares of a and b are always going to equal to the area squared of c, we can kind of move over to more of a visual proof that will really help the understanding of visually how the squares of a and b fit perfectly and are equal to the square of c. So here again we have a white triangle right here, and it's a 90-degree triangle. And so again, this side's going to be represented by a squared, and this side's going to be represented by b squared. And so by going up here and moving all of this over, it becomes clear that it perfectly fits and equals into the hypotenuse squared. So this area plus this area is going to equal this area. And what's interesting about this is if you were to say, oh, put this b squared into here and put this a squared into here, most people wouldn't know how to cut this up. This is these are some weird polygons going on, and so we're going to kind of show and explain how we got these shapes and why they do fit like this into the hypotenuse square. So now moving on to this figure, we are going to again, so this is going to be how we got these specific polygon shapes of a squared that are going to fit so perfectly into c squared. So the thing about the Pythagorean theorem is that it's actually, these can be looked at, a squared and b squared are part of a geometric pattern. And so we figured out that the Pythagorean theorem can be explained as being a part of a geometric pattern of tessellations. And so again, beginning with a right triangle, we create a squared. That's going to be represented in green. So that's step one. And then again, from our triangle, we're going to get b squared, and using this length. And so that will be, this blue square represents b squared. And then we're going to get c squared. So here's our hypotenuse. And so we're going to square the hypotenuse. Okay, so here's the total areas of a squared plus b squared equals c squared. And so c squared right here is what we're trying to fill in with a squared and b squared. So here we have part of a squared and part of b squared, but we need to fill them in geometrically with both. And so now we're going to bring a squared, the green, down here, and then we're going to look, and this is the space left that's going to be filled with the blue, the b squared. And so the last step, this pink is going to represent now kind of how we got these shapes. And this assignment also gave us the insight that any number squared will always form a physical square shape. So it's something very simple, but it's something that we never really acknowledged. You get anything squared and you know that it has a 2 above and that you multiply it by itself, but the fact that any number actually times itself is going to give you this times this, and it's going to create a larger area, and that's going to equal its square. And so for the design decisions that helped make us understand this concept deeper was definitely these colors. And so here, like, gray is going to correspond to gray, and the green is going to correspond to green. And so this really helps in the visualization that these are what translate over, and how they don't, you can follow them specifically and follow their locations to know exactly the transformation and translation that or the transformation that they're going through to get into this larger square. So that definitely helps organize the material. We thought that sliders were going to be very useful in this exercise, just to allow people to really kind of mess and see for themselves, oh, wow, look, yeah, no matter where I drag it, it always will equal each other. Figure out and watch carefully, maybe to think on their own, maybe why do these shapes fit, and if I cut it differently, would it fit, and is there any other ways to cut it in order to let this polygon 2, the purplish square, fit into this square.